Okay, so welcome to the quantum symmetry seminar. So today we have Ben Michael Kohli, from University of Bourgogne and from visiting BIMSA also. So Ben did his PhD in France with Peter Schwanberg and Emmanuel Wagner. And today he will talk about a lower bound for the genus of a knot using the Links-Gould invariant. So, Ben, the screen is yours.
Well, thank you. Thank you very much. And I'd like to thank you, Sebastian, and thank the other organizers for the opportunity to talk today. The work I'm going to be talking about today is something I did in common with Guillaume Tahar while I was staying in BIMSA in September of this year. And that's what I'm going to be talking about. So I'm going to be talking about the lower bound, new lower bound we found for the genus of a knot using a link invariant that's called the Links-Gould invariant. To do that, I'll first start by talking about knots, invariants in general pretty quickly, and then I'll give a general overview about the Alexander invariant. After that, I'll start talking about the invariant we're going to study, that is the Links-Gould invariant, and we're going to see why it's a generalization of the Alexander invariant. And finally, I'll go into details to prove today why that invariant gives a lower bound for the genus of a knot. So that's the idea. So first, let's talk about the objects. A knot is going to be an embedding of S1 into S3 up to isotopy. So that's what we're going to be talking about. And more generally, a link is going to be an embedding of a copy of S1s into S3, likewise up to isotopy. And often you can represent knots or links using diagrams. For example, this here is a diagram for the trefoil knot. That's the simplest non-trivial knot, and that's usually what we do, representing by drawing them with a diagram. And so the natural question is, if you have two links, two knots, how do you distinguish them? So how distinguish knots or links? And so, obviously, if you have two links, there can be two scenarios, or else they're equal, or else they're not. So if they're the same, how do you show that? Usually, well, you show that they're the same by actually finding an isotopy. You have to find an isotopy, make things explicit. But if they're different, usually how you're going to try to prove that is by finding a feature that distinguishes them. So you have to find a feature distinguishing them. And such a feature is usually what we're going to call a knot or link invariant. So a link invariant is such a feature that is a function, let's say phi, from the set of link types to a given set. And that's the general definition of what we call a link invariant. Of course, oh, that was a bad idea, huh? Sorry. Of course, you can define link invariants, some of them pretty easily, but the interesting thing is going to be to find link invariants that are both easy to define, or easy to compute at least, and that have a rich set of possible values so that you can actually distinguish links. I'm going to take a first example. So let's take an example. If you consider a link, so L a link, that link has diagrams, okay? And you can define the crossing number of the link as the minimum of the number of crossings for D taken over all diagrams for the link. Okay, so typically that's a link invariant. It's easy to define since I've just defined it, but it's very hard to compute. So this link invariant is in general hard to compute. Okay, that's a typical example. Things can be easy to define and hard to compute. And on the other hand, things can be easy to compute, but hard, don't distinguish lots of knots. That's another thing that can happen. Okay, I'm going to define now another link invariant that we're going to use extensively in this talk. That is the genus of a knot. And so from this point on, I'll be talking about knots and not about links in general anymore. Okay, and to define the genus of a knot, so if you set K a knot, we're going to define what we're going to call a Seifert surface for the knot. So what is a Seifert surface going to be? A Seifert surface is going to be orientable surface sigma with its boundary exactly equal to the knot. So sigma is a Seifert surface for K if the boundary of sigma is equal to K and sigma is an orientable surface. And so the claim due to Seifert is that actually for any knot such a surface exists. Okay, and this is due to an algorithm actually. If you take a knot, you can draw it using a diagram. And once you have that diagram, there's a systematic way to produce a Seifert surface. I'm going to take an example here. So let's draw a trefoil knot. So here we have a trefoil knot. We can try and draw a Seifert surface. So the first naive way to do that would probably be to do the following. Well, you take this part as a surface, and when you have a crossing like here, you take a strip that changes the orientation. The surface continues here, and then continues here. Okay, so that's a surface with its boundary exactly equal to the trefoil knot. The only problem here, if you do that, is that actually this surface here is not orientable. If this is oriented positively, this is oriented negatively, this is oriented positively, and you have a problem. Not orientable. And so you have to do here something else. Let's make another trefoil. Okay. And here I'm actually using the algorithm without explaining it because it's you don't necessarily have time for that. But if you take this part as the beginning of the surface, so you have crossings here, here, and here. And so each time I'm going to continue your surface here. And since it's not necessarily easy to draw things in S3, we're going to draw them in R3. And what happens here is that if this part is positively oriented, the other parts, this one, and this one are negatively oriented, and you're going to want that surface to go underneath the knot and to connect. Okay? And that, if you think about it, is a surface that has boundary exactly the trefoil, and this time it is oriented. Okay? So that's a Seifert surface for the trefoil knot. And once you understand that you can produce a Seifert surface for any knot, you can define the genus of a knot. Actually, quite in a similar way, we just defined another knot invariant. So what's the genus of a knot going to be? By definition, it's going to be the minimum among all genera of Seifert surfaces for the knots. So K Seifert for no. Sorry, sigma Seifert for K. Yeah. Right. So you have Seifert surfaces, you take the minimal genus amongst all of them, and you get the genus of knot. So that naturally is a natural invariant for the knot. And like in the case before, the problem is that in general, that genus is hard to compute. But still, and that's the first thing we can see, still, if sigma 0 is Seifert for K, well then the genus of K is smaller than the actual genus of sigma 0. So it's hard to compute, but it's not too hard to find upper bounds for the genus of a knot, right? And so in order to compute the genus for a given knot, what's going to be interesting is to find lower bounds for a genus, okay? What we want to find is a lower bound for the genus of any knot. Okay, just let's do an example of computing the genus for the trefoil knot. And to do that, I'm going to use this Seifert surface that we just explicited. So in general, the genus of a surface that's represented using disks and the strips is given by 2 minus the number of disks plus the number of strips minus the number of boundary components. Okay, and so here, if we look at what we divided by 2, if we look at what we had here, the number of disks we had on the Seifert surface was 2, the one on top and the one underneath. So that is 2. The number of strips actually is the number of crossings. So it's 3 minus the number of boundary components. There's only 1 because it's a knot. And so up, if everything is well, and it is, the genus of that surface is equal to 1. And so the genus of the trefoil is like that. All right. Now a little more topology, and after we'll get more quantum things. But so topologically, and that we have to understand, that is up to a homeomorphism, a Seifert surface can be obtained. What's happening? Sorry, well, let me change pages. A Seifert surface can be obtained by gluing strips to a disk. And since the Seifert surface is going to be bounded by exactly the knot, and it can be done in such a way that you attach strips to a disk, and that number of strips you're going to attach is linked to the genus. So if the genus of sigma is J, sigma can be obtained by gluing 2 times J strips to one disk in a way, and that's the only condition actually for it to work, in a way that there's only one boundary component. And so that can be represented in a canonical way, which I'm going to show now. That's image 1, right? In that way, actually. So if here you have your knot, you're going to have 2 times J strips, and that is a Seifert surface of genus J. Okay. And so once you represent things like that, you can also represent basis for the first homology group pretty easily by doing this. So that would be x1. That would be x2. And that would be x2j minus 1. And finally, x2j. Okay? So x1, x2g is a basis for the first homology group of the surface. Right. And the way x1, x2j actually are linked in S3, once you embed the surface in S3, gives us topological information about the knot. So produces topological information about the knot. Right. And in particular, one of the features of a Seifert surface is that it is oriented. So, but sigma is oriented. And since it's oriented, something you can do is you consider one of the generators. So if xi is one of the generators, well, that generator can be pushed forward in the direction of the surface to produce what we call a push forward. It's a curve that lives in the complement of the surface in S3. Is one of the generators. Xy can be pushed forward in the direction of the surface, producing the push forward of xy that lives in the complement of the Seifert surface. Okay, and that can be done diagrammatically. If you draw a diagram of the knot, I showed you that you can draw the Seifert surface, and you can actually draw the push forward on the diagram too. So all that is actually effective. Okay, and so that way, any xi and any xj pushed forward are non-intersecting curves in S3. And since they're non-intersecting, we can compute their linking number. So we're going to define Vij as the linking number of x, y, and the pushed forward of xj. What's the linking number? The linking number is the half sum of the number of positive crossings minus the number of negative crossings that between the two curves. So that produces numbers, and with those numbers Vij, you can produce a matrix. So the Seifert matrix, V is going to be the matrix containing all those integers, and so it's going to be a 2G times 2G matrix with coefficients in Z. Right. So first thing to see and to understand is that a Seifert matrix is not a knot invariant. It's not. But the important point is when you have knots, you can have a Seifert surface that produces the Seifert matrix, and with that Seifert matrix, we can define a knot invariant that's going to be the Alexander polynomial. So using all that, we can define Alexander polynomial of a knot in the following way. So you have your knot, you take a Seifert surface for the knot, and that Seifert surface produces a Seifert matrix V. And so if you take the determinant of T times V minus that transpose of V, where T is a formal parameter, this is going to be Laurent polynomial, an actual polynomial, but can be seen as a Laurent polynomial, in variable t. And this polynomial is what we're going to call the Alexander invariant for k. So in order for it to be not invariant, it has to be defined up to a sign and a power of t. So it is defined up to plus or minus t to the power n. And if you define it up to that, it becomes an actual not invariant. Okay? So that's the Alexander invariant. And for example, if you compute the Alexander invariant for the trefoil, using the Seifert surface I drew, for example, you're going to find t squared minus t plus 1. So that's the Alexander invariant for the trefoil knot. Right. The interesting thing about that definition is one of its direct consequences. That consequence being that if you consider, so you have a knot, you consider sigma, what is sigma j, a Seifert surface with minimal genus. So the genus of that Seifert surface is the genus of a knot. Well, looking at the definition of the Alexander invariant with that surface immediately shows you that the degree in variable t of the Alexander invariant of the knot is lesser or equal than 2 times the genus of sigma j, but the genus of sigma j is genus of k, so 2 times the genus of the knot. Why? Because the Alexander polynomials is a 2j times 2j determinant with each of its coefficients of degree smaller than 1. So if you compute the thing, you immediately see that the degree of the Alexander invariant is lower than 2 times g. So what happened here? Now, if we look at what we now have a lower bound for the genus of our knot using the Alexander invariant. And so often, not always, but often, that lower bound and an upper bound we find with a diagram allows us to actually compute the genus. Right. So that's to understand the objects and to understand what's at hand. So now I'm going to talk about the Links-Gould invariant of links and try and connect it to what we did now. Right. So what's the Links-Gould invariant of links going to be? So it's going to be a 2-variable Laurent polynomial. So in elements, let's say of z, t0 plus or minus 1, t1 plus or minus 1. It is a link invariant that is obtained by using the Reshetikhin-Turaev construction applied to Hopf superalgebra UQ GL2 1. So in general, you actually have a family of Links-Gould invariants, L, G, and M, with N and M in Z. Here we're going to only consider the simplest one in a sense. It's N equal 2, M equal 1. So when I'm going to be talking about the Links-Gould invariant, I'm actually going to be talking about LG21. Okay. So I'm going to explain that Reshetikhin-Turaev construction quickly. And in order to do that, we have to understand what an operator invariant is. So operator invariance. And in particular, we have first to understand what tangles are. So what is a tangle? I'm going to let the computer do a drawing. It'll be easier. So this one is obviously much too large, right? So what's a tangle? Well, for example, this is a tangle. So a tangle is going to be a set of curves embedded in a square such that you have a certain number of points at the bottom. So 3 points here, certain number of points at the top. Here, 1 point. And the curves connect those points, and you can do that in an oriented way, which we'll do here. So each curve has a orientation. Oh, I think here this is coherent. Right. So for example, this one, if we call it T, T is a 3-1 tangle, because there are 3 points at the bottom and 1 point at the top. And tangles like links will be defined up to isotopy. Well, not any isotopy. You're going to want to define them up to isotopy in the square that fixes the lower and upper points. So anything can move, but not the lower or upper points. And so that's a tangle. It's a actual drawn tangle up to that type of isotopy. A remark you can draw right away is that actually if L is a link, L is a tangle in that it's a 0-0 tangle. So links themselves can be put in that setting by the fact that they are 0-0 tangles. Okay. And what's nice about tangles is that they can, if you define two pretty simple operations on tangles, so set T and T prime two tangles. Well, there are two natural operations you can do on tangles. The first operation you can do is to put the two tangles next to each other. This is going to be called the tensor product of the two tangles. Just put them one next to the other. And the second operation you can do, if those tangles can be composed, is you can put one on top of the other. So that's not always possible. That's if they can be composed. And that will be the composition of T prime and T. Two natural operations. What's interesting is that any tangle can be seen as the composition using those two operations of a small set of very simple oriented tangles. So any tangle can be built from the following tangles using those two operations. So what are the elementary tangles going to be? Well, first, you have those two tangles going up or going down. Then you have the crossings. So for example, you have to make choices, but this would be a positive crossing. You'd have the negative crossing too. And you have to account for the fact that you're not only studying braids, but you are actually studying tangles. So you have to have caps, oriented caps, and cups that are oriented as well. Right? And any tangle can be expressed as the composition of such elementary tangles. And so the idea of operator invariance, is to take a tangle, let's say T, it would be an NM tangle, for example, and associate to that tangle a linear map So let's say Q of T and M. That'll be a linear map between a tensor product of n copies of V or V star, or a mix of the two, which I'll note like that. So the n is the number of strands at the beginning of the tangle. Two m copies of V or V star. All right. So you associate to a tangle a linear map, and to explain how, you just have to explain what you do on the elementary tangles, right? So, for example, so you have to make choices, but this can be associated to the identity map of V. And if you do that, the other one is going to be associated to the identity of V star. You have the crossings. For example, this one, the positive crossing, can be associated to a matrix that's invertible in V tensor V. And that map is usually referred to as the R matrix. Okay. You have the other crossing, the negative one, will be associated to the inverse map of R. And after you have all the cups and caps, for example, if you take this one, what you want it to go from V tensor V star to C. And that one we can call, for example, N. You're going to have the other orientation. So this one's going to go from V star tensor V to C. Let's note the N prime. And you have the cups. This one, for example, will go from C to V star tensor V. Let's call it U. And the last one from C to V tensor V star U prime. Okay. And you can associate that, you can make that association in a functorial way, which is the idea of the Reshetikhin-Turaev functor. Right. So if we do an example, let us do an example now. So let's take this simple link that's a tangle, and it is actually the unknot. How can we compute the operator invariant on it? So it starts in C, and then there's this first part here. It goes to, if you orient it like that, let's say you orient it like that. Okay, it goes to V star tensor V tensor V tensor V star. And the first map, counting for the first part, is U tensor U prime. Then we have the second part between the two lines. Still goes to V star tensor V tensor V tensor V star. And this is identity of V star tensor. Here it's R minus 1, I think. Tensor identity of V. And then I don't have any more room, but it goes to C using n prime tensor n. And that's the third part. So things, what I'm trying to say, are diagrammatic. You can compute the operator invariant using a diagram. Right. What we're going to require, what we require for the operator invariant, Q of V, is what we're going to call topological invariance. we are going to want that if two tangles are isotopic and you compute the operator invariant on those two different tangles, you're going to want the two maps to be equal, right? And in order for that to be true, you have to have a certain number of relations between n prime, u prime, and r. So this requires, oh, sorry, a specific relations between u prime, n prime, and r. For example, and I'm not going to draw them all, but for example, you're going to want what you call the Yang-Baxter equation. It is identity tensor R composed with R tensor identity composed with identity tensor R to be equal to R tensor identity composed with R composed with identity tensor R composed with R tensor identity. If you try to draw the Yang-Baxter equation, it's going to be something natural about three strands that will be part of topological invariance. Okay, but the question now could be, how do you produce such maps? So how produce n prime, u prime, and r such that you obtain an operator invariant? And the answer is, or at least one answer is, that if A is a ribbon, a super or not Hopf algebra, and if V is an A module and preferably irreducible, then there's going to be a systematic way to produce an operator invariant. And that systematic way is called the Reshetikhin-Turaev functor. Right. And so in order to produce all those maps, it is sufficient to have a ribbon, super or not, Hopf algebra. And the important feature of an operator invariant that you produce that way is that in particular, if T is a tangle, well, let's say an NM tangle, you're going to have Q, A, V of T is going to go from V tensor N to V tensor M. Well, it's obviously a linear map, but what more is that it is an A linear map. And that's going to be important. Is an A linear map. So representation morphism. Okay. So that's the general setting. The question would be now, our objective was to build link invariants. So how do you build? How do you produce link invariants? Using this, well, the first naive way would be to say, well, you take L a link, and you can compute Q, A, V of L. that works sometimes, but the problem you have most of the times is that number is going to be 0 for any link, not always, most of the time. And so when that occurs, this way of doing stuff doesn't work. You have to do something else, that is the following thing. So if you have a link, you can specify a point on that link. And what you can do when you do that is you can open the link at that point. And doing that, you obtain a 1-1 tangle. And if you do that, well, the operator invariant associated to the 1-1 tangle itself associated to the link is going to be a map from V to V. But it's going to be a linear map from V to V. And if V is irreducible A module, which most of the time it will be, if you use Shor's lemma, that proves that QAV of T is a scalar times the identity map. And this scalar here will be the link invariant associated to link L, right? And that's a way to produce link invariance. So examples of that, for example, if you take A to be UQ of SL2, you obtain, and well, a certain family of representations, you obtain the Jones polynomial. Okay, you can obtain Alexander as a quantum invariant by taking UI SL2 and a certain family of representations. Alexander can be produced as a quantum invariant. And what we're going to talk about today, what we are talking about today is A is UQ GL N M with a particular 1 parameter family of representations. That gives rise to the Links-Gould N M invariant. That's a 2 variable link invariant. And we only study here, we study what we'll call LG is LG21. Okay. The question would be, what's of interest using Links-Gould here? Well, the first thing is that LG is a generalization of the Alexander invariant. So how so? Actually in 2 different ways. If you compute LG on a link for T0 and you put the second variable T1 equal to 1 over T0, you're going to essentially find the Alexander invariant evaluated in T0 square. That's due to De Witt, Ishii, and Links in 2005, I think, maybe 2006. And there's another way to recover Alexander using the Links-Gould invariant. If you put the second variable equal to the opposite of the inverse of the first one, you actually find the square of the Alexander invariant. That's something I did with Bertrand Patureau-Mirand. It must have been published in 2018 or something like that. Right, so you have 2 different ways of producing the Alexander invariant if you know the Links-Gould invariant. So that means that the Links-Gould invariant generalizes the Alexander invariant, but it also raises questions as to, you have properties for Alexander, you have some classical properties that come from the classical construction I just explained, and you could wonder, do any question. Do any, sorry. Do any of the classical or not, but in particular classical features of the Alexander invariant also happen with LG? And there are a range of conjectures. There's a range of conjectures answering positively to that question. In particular, we anticipate that the Links-Gould invariant should act like Alexander with alternating links. It should act like Alexander on fibered knots. And now we know, because that's what we proved with Guillaume. So that actually the lower bound for the genus of a knot that we obtain using the Alexander polynomial that I explained before can be enhanced systematically using the Links-Gould invariant. So if you look at the degree of that Links-Gould polynomial respective to one of its variables, that's can be noted q to the power alpha on a knot, it's going to be smaller than 4 times the genus. If we look at the two evaluations we have, that's what you could suspect, and that's what you find for a lower bound for the genus of the knots in the specializations. But what we're saying is that it's actually true in general without specializing. And that's what I'm going to prove right now. A quick thing about variables: you can express the Links-Gould invariant using 2 different sets of variables. One that's q and q to the power alpha. The other one's that's t0 and t1. T0 and t1 is more practical for using the Links-Gould invariant to compute stuff. But q and q to the power alpha is the set of variables that you use if you build the Links-Gould invariant. In essence, q, this variable here, is the variable that comes from the algebra itself. The algebra UQGL21 has relations, and the relations that q appears in the relations of the algebra, and so it appears in the invariant. The other variable here, q to the power alpha, accounts for the fact that to build the Links-Gould invariant, you do not use one representation v, but a family of representations v alpha. That's a continuous family of representations, and that's q to the power alpha is the parameter accounting for the family of representations. Okay, so we're going to try and give a sense of why this theorem is true. And to do so, we're going to come back to topology a little bit. So we said at the beginning that when you have a knot, and that's what we're going to be considering here, when you have a knot, that knot that is here on the drawing, that knot can be the boundary of a Seifert surface, and we suppose that the Seifert surface here of minimal genus, so that there are 2 times the genus of K strips here. So that is abstract, this drawing, in the sense that it's up to homeomorphism. But the fact, and the actual interesting fact, due to Abiro, is that this drawing that we just did can be embedded in S3 in a pretty direct way that I'm going to explain now. Actually, what Abiro states, and that we use, well, he doesn't state exactly that, but it can be interpreted in that way. What Abiro states, I'm trying to fight with this thing there, okay. What Abiro states is that the embedding of the Seifert surface in S3 can be done in a way that generally it looks like the non-embedded surface, and that all the knotting information can be stored in that rectangle that I just drew, in the sense that those strips that you have abstractly can contain, in the way they're entangled, all the knot information, right? And so you can take an actual drawing like that as the drawing for the knot embedded in S3. Right. And so if you do that, you can try and start computing things. And in particular, you can take a point here on the disk, and you can open your link at that point. And if you do that, you obtain such a 1-1 tangle that I'm going to draw now. It's image 4. So this here is exactly what you obtain if you open the previous image at point P, right? With all the knot information contained. With all the knot, I'm trying to make this work, right? With all the knot information in here, and with, so, 2G strips here. Okay. Right. And what we can do to simplify how we're going to compute the operator invariant is actually take that rectangle and pull it using topological invariance to pull it in this direction over here, which I'm going to draw now. This is image 5. What I'm saying, in essence, is that we can compute operator invariance on knots using a very specific type of diagram. Right. And here is the diagram that interests us. Here it is. So we pulled the black box part to the bottom. And so as an operator invariant, that black box part that I noted f of k is going to be a map from C to V alpha tensor V alpha star to the power, to the tensor power 4 times j. For each genus, there are 4 copies of V or V alpha. Okay. Right. And so how does that help us compute lower bound for the genus of a knot? That's what we're going to try and understand. And that's where representation theory actually kicks in. What we have, and that's an important lemma, what we proved. So we have this representation of UQGL21 that has one parameter that gives rise to one of the variables for the Links-Gould invariant. What you can do with that representation is tensorize it with its dual representation. And what happens when you do that is actually that V alpha depends on alpha, V alpha star depends on alpha, but if you tensor them together, the module you obtain does not depend on alpha, meaning that you can choose a basis for V alpha tensor V alpha star, in which the representation of any generator of the algebra as a matrix, for example, does not depend on alpha. And so that says as UQ GL21 modules. And that's going to have actually pretty important consequences for the way we compute the invariant. So this lemma can be understood pretty straightforwardly in a theoretical manner, but if you want to compute stuff, you have to make all that explicit, and that's actually what's pretty hard, is to find an actual explicit morphism. So that's what we've done. And once you've done that, so I know I'm a little bit over, maybe have 5 more minutes. That's okay. Once you've done that, this means that in the diagram, when you have something like that, V alpha and this V alpha star, this can actually be replaced by this, okay? And likewise, when you have this and this, so V alpha star tensor V alpha, it can be replaced by, no, can be replaced by this, right? And that uses the naturality properties of the Reshetikhin-Turaev functor. And therefore, and that's going to be the last diagram I'm going to show, and the one we're going to actually use to compute everything. This means that we can compute things on the following last diagram I'm going to show. It's this diagram that here is much too large. Still much too large. Right? Okay. Where the boxes that I called B and C are the following things. So, you start with V alpha here. You go out with V alpha. And with boxes B and C, you translate the fact that you have morphisms from W to V alpha tensor V alpha star. And that morphism is box A, what's called A here. And likewise, you have isomorphism from W star to V alpha tensor V alpha star. And that's the box that's called A tilde. That's right here. But so in essence, boxes A and A tilde transform V alpha tensor V alpha star into W. And this means that all this part in the diagram does not depend on Q to the power alpha when you compute things. And so using the fact that LG of R naught times identity of V is equal to the operator invariant computed on that tangle T that we've just drawn. One way to compute LG is to take a vector V in V alpha and to try and understand what happens when you compute that map and what happens to V when it goes through that map, actually. And what happens to V when it goes through that map? Well, first it goes through box B, then it goes through a box B, then through a box C, and then through a box C. And that's each time that there's a genus. So G times that, B, B, C, C. But since that part J of K does not depend on Q to the power alpha, the degree in Q to the power alpha of the Links-Gould invariant at the end only depends on what happens when it goes through box B, box B, box C, and then box C, G times. And that's to say, and I'm not going to go into details, but that's to say that if you can control the genus for a box B and for a box C, which is essentially computing the matrices of those two boxes B and C, you can at the end of the day control the genus, control the degree of the Links-Gould polynomial in terms of the genus. But that is entirely due to the fact that you can render all that part J of K as not depending on the variable that's of interest to us. Okay, and so doing that precisely proves that the degree in Q alpha of our Links-Gould invariant of K is actually smaller than 4 times the genus of K, which is a systematic way to get a lower bound of the genus that is systematically better than that using Alexander. That's the classical lower bound. Just 10 more seconds. If someone asks me a question about that, I can answer, but a real question is, well, you've done all that. Is this bound actually really better than the Alexander invariant? It could be that it's always exactly the same bound. So that's not the case. There are cases, and there are interesting cases actually, topologically, where the Links-Gould invariant enhances the bound for Alexander and enhances the information you get. Thank you. Sorry for being 9 minutes over, and I'm finished. Thank you.
Okay, thank you. Thank you very much.
Thanks.
So, any question online or offline? So people want to ask question of online, they have to unmute. But let me start.
Sure.
So let me start by some general question.
Mm-hmm.
So about this computation of the genus of a knot. For example, do we know the genus of the Conway knot? Because I know that the Jones polynomial was used to distinguish Conway knot, or if I'm not mistaken. So this Conway, no, it's not true. So you can correct me
no.
then on that.
Right. Well, it's interesting. That's something I actually was planning to talk about. And if I may, I'll project the Conway knot and its counterpart, the Kinoshita-Terrazaka knot. Yes, and I'll explain your question. I mean, in the sense that why is that important? What image is that?
So the question is it the
Yes.
genus of the Conway knot known?
Yes. So let's just project first the Conway knot. So actually, the Conway knot is
So you should
part of
share
an
your
interest.
screen again.
Oh, sorry. Yes. Pop. Partager l'écran. Partager.
Yeah.
Great, thanks. So the Conway knot, I think is this one. So it's a knot with 11 crossings, and it's associated to what we call the Kinoshita-Terrazaka knot. There are two 11 crossing knots, and in the classification of small prime knots, they were the pair of knots that were most difficult to distinguish. And to answer your question, the Conway knot and the Kinoshita-Terasaka knots, if you take the Jones polynomial, it doesn't distinguish them. If you take the Alexander invariant, it doesn't distinguish them. If you take the Jones polynomial, it doesn't. And even if you take the Links-Gould invariant, it doesn't, because in theory, if you have a quantum invariant, in the way that a quantum invariant is built, it'll never distinguish mutation. And the Conway and Kinoshita-Terasaka knot, they're linked by mutation. So no, the Jones polynomial doesn't distinguish Conway and its mutant. Alexander doesn't. We know that from the beginning, but we also know it because it's a quantum invariant. And even the Links-Gould invariant does not distinguish those two knots. Still, the other problem with the Conway knot and the Kinoshita-Terasaka knot is one of them, I don't remember which I'm doing it. It could be the contrary, but one is genus 2, the other is genus 3.
Okay.
But what happens is that all the simple classical tools you have to compute the genus of a knot, explicitly the Alexander invariant and what we call the Levene-Trinstrom signature, they don't even detect the fact that those two knots have genus. So for example, if you look with Alexander, the Alexander invariant of KT is equal to the Alexander invariant of Conway, but it's equal to 1, which is the Alexander invariant of the unknot. So if you try and use the lower bound for the genus that's given by Alexander, Alexander does not even detect the fact that those two knots have genus. Same thing for the Levene-Trinstrom signature that I don't want to talk about right now, but if you compute the Levene-Trinstrom signature on those knots, you find 0, which would be the case if it doesn't have any genus. But from that perspective, if you compute LG for KT or for Conway, the general theory tells you those polynomials will have the same Links-Gould invariant, so they're not distinguished by Links-Gould. But if you take the degree of LG for those knots, it actually shows you that the genus of those two knots is greater or equal to 1.5. But since the genus is an entire number, that proves that the genus of KT and the genus of Conway are larger than 2. So the Links-Gould invariant does detect the fact that those two knots have genus and have non-trivial genus.
So the Jones polynomial what was the link between Jones polynomial and Conway? He can help to distinguish Conway from the unknot, maybe, no? So what was the
Yes, that's right. Yes.
Whereas Alexander cannot.
Whereas Alexander cannot.
Okay.
Yes. Maybe that was your question, but okay. Yes, that's true.
No, but it's okay. Okay. So if someone has a question, can unmute. Otherwise, I can.
There's one. There's a discussion.
Yeah, but I guess it's something called. Let me check. Some whole thing. Yeah. So I have other questions, so I can continue. But if someone else wants to ask before, well. So let me continue then. So yeah. So what about the? Okay. So you said the genus is very hard to compute. But at least you show an example, so you already answer my question. The genus can distinguish these two example.
Yes.
So one question is, so you talk about tangle. So do you know about planar algebra or something like that? Subfactor planar algebra? Because I come from subfactor planar algebra, and have you heard about that? Planar algebra, Jones planar algebra.
I've heard the name, but I don't know exactly what it refers to.
You are not specifically interested in?
No.
Okay. Yeah, so the question is, so you said the Reshetikhin-Turaev invariant for not or for links involve category of representation of Hopf or super Hopf algebra with some specific properties. So what about considering general tensor categories for such invariant? So
the problem with considering something much more general would actually be producing the maps. In particular, when you have a Hopf algebra, you cannot, in general, in a systematic way, produce an R matrix. That's why you have to say you have a ribbon Hopf algebra. In essence, saying you have a ribbon Hopf algebra is saying you have something in the Hopf algebra that will project to an R matrix when you represent stuff. So the real problem is the R matrix, and usually the way you provide a universal R matrix that projects to R matrices once represented is just you give an explicit formula. So that's the real problem. And if you want to put things more generally, you probably can, but that problem of the R matrix remains.
Okay. So what about if you consider braided tensor category or modular tensor category? Maybe that can help.
If you have something upstairs that acts like a universal R matrix, yes.
Okay.
But that has to be explicited each time, right?
Okay. And so the LG invariant you mentioned is about a specific super Hopf algebra. I don't remember.
Yes.
So why this one? Why did this one was choose specific one, and why is this one and not another one?
Well, first because you have specific representations, highest weight representations in that algebra, and you have specific highest weight representations that are pretty small in dimension. So that everything's relative. But for example, if you to know how complicated a quantum invariant, a quantum link invariant is going to be to compute, if you look at it only as a quantum invariant, essentially, it's going to be complicated if the dimension of the vector space is large. And so, for example, for Alexander and for Jones, you have two-dimensional vector spaces. And so after the R matrix, for example, itself is 4 times 4. So 16 coefficients. For LG21, the underlying vector space is already 4-dimensional. Okay. And so, for example, if you try to compute the R matrix, it's a 16 times 16 matrix. And so things can get pretty out of control if N and M become large. But for that family, at least, of representations in GLNM, you have highest weight representations, which is nice to compute things. Well, relatively nice, nicer than if they were not so structured, those representations. And it just to say something about that, that is a motivation of what we're working on. That invariant LG remains pretty hard to compute, to be honest, because the matrices are large, because if you want to do stuff computationally, you have to put the diagram in a specific form, etc. The idea of trying to find a more classical interpretation of LG is also to make it more computable.
Okay.
Right.
So this LG invariant was defined when?
It was defined in 1992 by John Links and Mark Gould. 92, but it became clear that it could be computed using the Reshetikhin-Turaev theory in 1999, I think, when Kaufman visited them and told them that actually you could present stuff in a more algebraic setting. Yes. So in that form I presented, it's 1999.
Okay. And so the theorem you proved helped to improve the bound for the genus. So it's you have something better than what you can do for Alexander polynomial with the LG.
Yes. Yes.
So
Since
do you have,
yes.
do you have an explicit note for which you can compute the genus thanks to your theorem, whereas it was not known before or something like that?
Well, not really, because since Kovanov introduced his Kovanov homology, if you compute Kovanov homology, which is hard, but which can be done using a computer, there's a way of computing and knowing the genus of a knot, a straightforward way. And that's actually in knot tables, that's how they completed everything, is using Kovanov homology, putting a strong computer at work. And if the computer works, it produces the genus.
So the genus are known up to which number of crossing?
If you go on knot info, I think now they have them for all knots, all prime knots with less than 16 crossings. I think
6-0?
16. Yes, which is already like more than 1 million knots. Prime knots.
Okay.
But in theory, if you have a knot and you have a computer, the Kovanov homology theory will give you the genus. But the idea still is not, well, in my perspective, at least the idea is not here essentially to make things more computable. It is that it is to understand a quantum invariant from a classical perspective.
Okay.
And because like when the Jones polynomial appeared, all that quantum theory just unrolled. We managed to interpret Alexander as a quantum invariant, but things have not been so natural the other way, like taking all the quantum invariants and understanding them from a classical point of view. We believe that this invariant is the right one to try that, because it's close to Alexander, and things can be traced using the evaluations that give Alexander. So that would be the idea, to take that quantum invariant and to manage interpreting it from a classical perspective.
Okay.
Which who knows, after could maybe open a way to understand Jones from a simple classical perspective. I don't know, but I mean, that's the idea. That's the idea.
Okay, so okay, so if there is no more question, let's thank you again.
Thank you very much. Thanks.
Thank you very much. So I will stop the recording.
Right.